In this video, we're going to cover section 5.4, which is the fundamental theorem of algebra. We're going to talk about this theorem. We're going to talk about what it means when we have repeated zeros, what conjugate pairs are, and just kind of a summary of some polynomial methods with a few examples. So the fundamental theorem of algebra tells us that if we have a polynomial p of degree n, and n is greater than or equal to 1, then p is going to have at least one zero. Remember, that's where it crosses. That's where the function is equal to 0. That's a value of x where the function is equal to 0. And it's important to note that that 0 of p, and essentially the value of x that makes your function equal to 0, might not be a real number. So if the value of x that makes your function equal to 0 is a real number, then we cross the x-axis. But there are solutions to this equation that are not real numbers. So they're imaginary numbers, okay, or complex numbers. So if we have a polynomial of degree 1 or greater, we can always factor it. We can always factor it into linear factors. And we're going to have n linear factors. They might be repeat factors though. These are going to be real factors, they're going to be factors, but they might not be real numbers. They might be imaginary or complex numbers, okay? And they might not be distinct. Nevertheless, an nth degree polynomial can be factored as a product of n linear factors. They just might not be real and they might not be unique. So this doesn't tell us that they have how many real zeros a polynomial has. It doesn't tell us how many zeros are distinct, meaning they could be repeat. It just tells us that we can write it as a product of linear factors. It doesn't tell us what those factors are. All right. So how to interpret this linear factors theorem is basically says, if we have an nth degree polynomial, we're going to have n factors, but they might not all be real, and some of them might be repeats. So that means that we can cross the x-axis at most n times. And it means that we're going to have at most n minus 1 turning points. So just remember, a linear equation never turns. A second degree equation has one turning point, okay? So an nth degree polynomial has at most n zeros, okay? So what does multiplicity of zeros mean? A multiplicity of zeros just means that the same linear factor is repeated. If we have a linear factor, say x minus 2, but x minus 2 is raised to the third power, then that counts as 3 of our zeros when we're trying to count how many zeros we should have equal to the degree of the polynomial, but they're actually repeating. So those are multiplicity zeros. And we say that a factor has a multiplicity of k, where k is the exponent on that factor, or the number of times that factor repeats, okay? Geometrically, when we have a repeat linear factor, what's going to happen is that the graph is going to touch the x-axis at that point. And if that factor, if the number of times that factor occurs is even, then we'll go through the x-axis. But if the number of times that factors occurs is, if it's odd, we go through. If it's even, we're going to stay on the same side. So I think it was 5.1 where we had 3 factors, but it only actually crossed the x-axis once, and it just touched at another point. So if you have a repeat factor, it just touches and turns around, okay? So if you have a second degree, fourth degree, or any odd multiplicity of a 0, it's just going to touch the axis there and then turn around. versus if you have an even factor, it'll turn around. If you have an odd factor of zeros, if your multiplicity of zeros is odd, it's going to go through the axis. Okay. Also, anytime the multiplicity is more than 1, the graph is going to flatten out right near that 0. The conjugate roots theorem. So if we have a polynomial with real coefficients and the complex number is a 0 of our polynomial, then so is its conjugate. Basically, all of our complex zeros are going to come in pairs. If we have an a plus bi is a conjugate, is a 0, then a minus bi is also going to be a 0, right? So anytime you have one complex number, its conjugate is also going to be another 0. So let's do just 2 examples here. We've got some pretty big polynomials, and we're going to find their intercepts, factor them, and sketch the graph. So our first example, we've got this 4th degree polynomial. What we know about this polynomial is we know its end behavior. Since it's even, its end behavior is going to be positive and positive. It's even and positive. We know that it has at most 4 zeros. All right, so we have at most 4 zeros. So the number of zeros is less than or equal to 4. And we know that the number of turns is going to be less than or equal to 3. Okay. So we can imagine if it has positive end behavior on both ends, we can turn 3 times and we can have 4 zeros. Or maybe we only have 2 zeros, or maybe it kind of does something like this, where we just have these 2 zeros. So we know our function can kind of look like any of these things, or it's possible that our function does this and has no zeros. So those are kind of our possibilities that we've learned from these different theorems. Okay. Again, we can go through the axis twice. We can go through the axis not at all, or we could go through the axis 4 times. Okay, that's what we know based on the degree of this polynomial. Now, in order to figure out where this does cross the x-axis, we're going to need to factor it. To figure out what some of its factors might be, we can use Descartes' rule. We can figure out how many rational zeros we are using the coefficients of the leading and the final term. And we can find the upper and lower bounds of these things. So let's start by just listing what all the possible rational zeros are. Since our leading coefficient is 1 and our constant term is 12, that means all the possible rational coefficients are going to be things like, are going to be factors of 12. So we're going to have 12, 6, 4, 3, 2, and 1. And we're going to have all the positives and minuses of these. So that's 12 different possible rational zeros that we have. If we want to figure the bounds on our real zeros, we could plug this in and plug in one of these to guess at an upper or lower bound. We can also figure out how many positive and negative zeros we have using Descartes' rule. So if we start with Descartes' rule, we can see that f of x changes sign here and here. So that's twice. So if f of x changes twice, then we have 2 or 0 positive real roots. And then let's take a look at f of negative x and how many times does that change sign. F of negative x is going to be x to the fourth minus x to the third minus 8x squared plus 6x plus 12. So f of negative x changes sign twice also. So we've got 2 or 0 negative real roots. Right. So from here, we could try to look at some bounds, but we could also just try to eliminate some of these roots. Since we have a fourth degree polynomial, it's possible we have 2 real positives and 2 real negatives. It's also possible that none of them are real. So let's just start by checking to see if, let's say, x is 1 is a root. So we're just going to do synthetic division where x is 1. So I've set up synthetic division to check if it's possible for x to be 1, which would mean that x minus 1 is a factor of this polynomial. Okay. So 1 times 1 is 1. We're going to add those together. Um, 1 times negative 8 is negative 8, and we get a 4. Oops, that is supposed to be a 6 right here. See how that changes things. All right. Yes. 1 times negative 6 is negative 6, which gives us negative 12 here. We have a negative 12 and we get a 0. Having a 0 in this position means that this is a factor. So we can factor that out. So now our f of x looks like x minus 1 times x to the third. So this is our coefficient here, plus 2x squared minus 6x minus 12. Right. So we found one factor of our polynomial. Now we want to go further to find the other possibly 3 factors. I can see that we can factor what's remaining here by grouping. So let's factor this stuff by grouping. So if I group the first 2, they've got a factor of x squared that they share. And if I group the second 2, they've got a factor of negative 6. And all that stuff will factor to x squared minus 6 times x plus 2. Plus our original factor. And now we've got 2 linear factors and 1 nonlinear factor, right? So we can see that x can equal 1, or sorry, x can equal, yes, x can equal 1. This is a positive. X can equal 1. X can equal negative 2. And then for this last factor, we've got x squared minus 6. Well, what values of x make this equal 0? That is when x squared equals 6, which is when x equals plus or minus the square root of 6. So we've got x equals the negative square root of 6 and x equals the positive square root of 6. That gives us 4 zeros, and those are 4 linear factors to our equation. Now that we have these 4 linear factors, and notice that all of them are multiplicity of 0. or sorry, multiplicity of 1. Let's rewrite this in a completely factored form. So now we've got our function f of x is x minus 1 times x plus the square root of 6 times x minus the square root of 6 times x plus 2. These are all multiplicities of 1. And since the multiplicity is odd, that means that for each of these, we actually go through the x-axis. They don't just turn at the x-axis. So if we want to graph this function, we've got our +1, we've got our -2. The square root of 6 is a little bigger than 2, but smaller than 3. So we're going to have our positive square root of 6, our negative square root of 6. And these are kind of our 4 points that we go through the x-axis. Now we also remember that this was even and had a positive leading coefficient. So we know that our end behavior is positive. So we can, without even testing the inequalities, since we know that the multiplicity of each of these roots is odd, or it's just 1, we know that it's going to go through the axis at each of those points, and we know the end behavior. So we know our graph is going to look roughly something like this. Now it's true, it could look like this, or any kind of extremes there. We don't really know where the turning points are, but we do know when we go through the x-axis, and we know where our graph is positive and negative. Okay. And just to recap, we used all those tools we just learned. We used all those tools we just learned, like the rational roots theorem to tell us some rational roots. We used Descartes' rule of signs to tell us how many possible negative and positive. And that was in hopes, really. Descartes really was just in hopes that we could eliminate the possibility of negatives or positives. So Descartes didn't help us too much. And we used what we know about the fundamental theorem of algebra to tell us that we have 4 or less possible zeros and 3 or less possible terms. And then finally, when we graphed, we said because the multiplicity of each of these is 1, we know that it's actually going to go through our axis at 1. So we didn't even have to test those regions. Let's go on to our next example. All right, so let's talk about what we know about this function. The rational roots theorem is going to tell us that we have our only roots only rational roots. Remember, there can still be irrational or complex roots. Our only rational roots are going to be plus or minus 9 and plus or minus 3 and a plus or minus 1. All right. We also know that our end behavior, since we are 5th degree and our polynomial is positive, it's going to be negative as we go to negative infinity and positive as we go to positive infinity. All right. We can take a look at Descartes' rule of signs. And we see that our f of x is going to change sign, let's see, once, twice, 3, 4 times, 4 times. So we have either 4, 2, or 0 positive reals. And our f of negative x, you guys can do this on your own, but it changes sign 1 time. So we're going to have 1 negative real. Right. So that's the information we have. So knowing all this information is actually really helpful this time. We know that we have 1 negative real. So we are definitely going to want to start by checking for the -9, the -3, or the -1. Easiest is going to be this -1. So we're going to do long division on the factor of -1, or essentially we're dividing out x plus 1, but we're going to use synthetic division because it is a linear factor. So let's set up our whiteboard. If we want to do the factor -1 and our coefficients are 1, -1, -8, switching this around, 1, -1, +8, -8, -9, +9. Okay, set our line here, drop this guy down, and go through our long division. -1 times 1 is -1. That gives us -2. -1 times -2 is 2, which gives us 10. -10 gives us -18. -1 times -18 is a +18, which gives us a +9. And -1 times 9 is -9, which leaves us with 0. Oh, good. That means x plus 1 is a factor. And we can rewrite our f of x as f of x equals x plus 1. Oops. X plus 1 times x to the 4th then we take our next coefficient, -2x to the 3rd plus 10x squared minus 18x plus 9. So we took our 5th degree polynomial. We found one of the roots, we factored it out, and this is what's left. All right, now we've got a 4th degree polynomial we need to work with, and we can do the same thing. So notice with this polynomial, we have the same constant term and the same leading coefficient. So it doesn't narrow down the possible remaining roots any. We could also use Descartes' rule, but we already know we have 1 negative and 4, 2 or 0 positives. So the next step would probably be, do we want to try to find some bounds? Do we want to maybe check if what we have left for our positive reals? So our positive rationals, since we've already found our 1 negative root, our positive rational roots can be 9, 3, or 1. All right. We can start with 1 since it's easy. So we're going to do synthetic division on the 1, and our coefficients are 1, -2, 10, -18, and 9. We'll bring down our 1. And indeed, 1 is also another factor of our polynomial. So we've got x plus 1, x minus 1, and then let's look at our coefficients. We've got x to the 3rd minus x squared plus 9x minus 9. We are now down to a 3rd degree polynomial. We can actually look at this guy and factor it by grouping. We can factor out an x squared here. So this is going to be x squared times x minus 1. And we can factor out a 9 here. So this is going to be 9 times x minus 1. That will all factor to x squared plus 9 times x minus 1. Notice now we have 4 factors. The x minus 1 is a repeat factor, and the x squared plus 9 is a 2nd degree factor. let's take it to the side and do this x squared plus 9. If we set that equal to 0, we get that x equals plus or minus the square root of -9. So x is going to be plus or minus 3i. Well, that breaks this guy into 2 more factors. So now we have one factor of x plus 1, 2 factors of x minus 1, and a factor of x plus 3i, and a factor of x minus 3i. So our function f of x is going to equal, we've got our 2 factors of 2 factors of x minus 1, 1 factor of x plus 1, and then we've got a factor of x plus 3i, a factor of x minus 3i, and what was our other factor? That is going to be 5. Yeah, that's our total factor. So we've got 5 total factors. Notice that the factor where x equals 1 is repeated. Okay, that means when our function, when x is equal to 1 and we touch the x-axis, we're actually going to turn at that point. So let's take a look at what this means. When we graph this guy, we have x equals 1 as a point. We have x equals -1 as another point. And then these are imaginary, so these are not crossing the x-axis. We also know that our end behavior is going to be like this, since it is an odd polynomial with a leading coefficient that is positive. But we know that right here, we're actually just going to touch the x-axis and turn, because that is of even degree. So what it's going to look like, we're going to go through our x is -1. We're just going to touch this guy and we're going to turn, because we're of even degree there. Right? So that's graphing, finding the zeros of our second example. Take some time, maybe go back over this so that you understand each piece. I know I went through it pretty fast. Use the discussion board if you are getting stuck, and email me if you need some office hours. All right, good luck.